In the last video, we started to talk about the idea of measures of spread, and we talked about how important it was that you always accompany a measure of location, like the median, with a measure of spread, such as the interquartile range, because the two go together, because the median tells you where the centre of the data tends to be, whereas the interquartile range tells you how spread out it is. And two sets of data might have the same median, but might have a very different spread, which helps you to see the differences between the sets of data. Now, the interquartile range is generally paired with the median because they're calculated in similar ways. However, if you are working with a mean, you use a different measure of spread, and a measure of spread that is dependent upon the mean in order to work it out. Now, in order to kind of convey the idea of what this measure of spread is, we're going to look at this set of data, which is the same as the one I used at the start of the previous video. The mean of this data, these data, is 14. So if we call the data x, then x bar is 14. Now let's look at how spread out each of these data values are from the mean. This one is 1 back. This one is 2 back. This one is 1 forward. This one is 2 forward. So if I wanted to talk about the spread from this mean here, I might be tempted to, I don't know, say find the average of all these different spreads. Now, the only problem with that is the fact that some of them are negative and some of them are, I should have written 2 there, some of them are positive, which means the negative ones and the positive ones. If you were to find the average, as in the mean, of these, you would add them together and divide by 4, but the positives and negatives would cancel each other out, and you would end up with 0, and that's not particularly useful, but the idea is still useful. So this is what we do. We work out how far each of these values are from the mean, and then to get rid of any negative values, we square all of these differences. So this difference gets squared to give us 1, this one to give us 4, this one to give us 1, and this one to give us 4. And then what we do is we add up all of the squares of these differences from the mean, and we find the average of those. So we go 1, add 4, add 1, add 4, divide it by 5, because there are 5 data values, and that gives us a measure that we call the variance. So we write it mathematically like this. So we've got the x values minus the mean, so that's the difference between each of the x values and the mean. We square each of those differences, we sum up all those squares, and we divide it by how many data values we're dealing with. And this gives us a really good way of considering the variance, as in the spread, how much the data values vary from the mean. This has units, just like the measures of spread in the previous examples, the previous video did. But the problem is, because we've been squaring here, the units of this would be the units of our data squared. So if our data was, say, time measured in seconds, then the units of the variance would be seconds squared. Now that's not particularly useful. It's nice to have the units of our measure of spread being exactly the same thing as the units of our data. So we jump from here to a measure called the standard deviation, and that's simply the square root of what we just found out, the square root of the variance. So this one is the units of the data squared, and this one is just in the units of the data. So this is the one that you'll see talked about the most. This is the most common one, but you can't work this one out without working that one out first in order to square root it. Now there are other ways of writing or finding the variance. They're all the same thing, it's just that this formula can be rewritten in lots of different ways, and some of the ways are more useful than others in different scenarios. So one of the ways we can rewrite this formula is we can take all of our x values, these are the x values, we can square them, and we can add all those squares up, divide it by how many values we've got. Then we work out the mean of these x values, so x bar, which is that, and square it. So I could also have written this as the sum of x squared over n minus the mean squared, like that. That's another way of working out the variance. These two formulae are exactly the same. It can be proved. I won't do it in the video. If you really want to know how it's done, go see Mr. Bick. He loves proving this one. Now, another way of doing it is using a very simplified formula that looks like this. But SXX is what we call a summary statistic, and it's just a short way of writing this here, the sum of the squares of the differences from the mean. Now, your calculator gives you this. So, and sometimes exam questions will give you this as well. So it's important that you know that the variance can be found by dividing this, which is called SXX, by n. Now, of course, if the standard deviation is the square root of the variance, then all of the versions of this can just be square rooted to give us 3 different versions of the standard deviation. So we could say, for instance, that the standard deviation is the sum of the squares of the x values minus the mean squared, or we could say it's the square root of SXX over n. And all of those are just 3 different versions of the same thing. And what it measures, this standard deviation, is a measure of the spread of the data values from the mean. So it's taking the mean as the centre and it's saying, on average, how spread out are these values from the mean? So the bigger the standard deviation is, the more spread out the data are, and the smaller it is, the less spread out the data are. So let's have a look at it in practice, and then I'll show you how you can calculate it, or you can find it on your calculator much more quickly as well. So we have got an example 7, the marks of 7 students in a test. We've got to find the variance and the standard deviation of these marks. I'm going to use for the variance the second formula here, because when you have raw data, this formula is the quickest one for working it out. That one just takes forever and it's annoying, so this is the one to go for. So what we're going to do first of all is find the sum of the x values. That means just add up all these x values. Let's do that quickly. 3, 4, 6, 2, 8, 8, 5, it's 36. Now what we're going to do is find the sum of the squares of the x values. Now that, be careful, that doesn't mean square this. What it means is square each of these and then add it up. So we're going to go 9, add 16, add 36, add 4, add 64, add another 64, and add 25. So that's 218. Once we've got both of those, we can find our variance. Let's go move the calculator out of the way. The variance formula here is the sum of the squares divided by n minus the mean squared. So we've got 218 over, what was it again, 7? 1, 2, 3, 4, 5, 6, 7, yeah, minus 36 over 7, add them all up, divide by 7, that's the mean, squared. So our variance comes out as 218 over 7 minus 36 over 7 squared is 4.69. These were test marks, so there's no units here, so we could just say a variance of 4.69 marks squared here. And then, of course, the standard deviation is the square root of the variance. Now, I'm not going to type in 4.69, I'm going to keep this number on the calculator and I'm just going to go square root of that answer is 2.17 to 3 significant figures. So let's think about what that means on these data. I'm just going to make a note of what the mean was there. It was 36 over 7, so that's 5.14 marks. So for these data, these 7 test results, we can say that the mean test result was 5.14, but the average spread of all the marks from that mean was 2.17. And you can kind of see it when you look at it. If you look at the data, it'll probably help if we wrote them in order. I'll leave that as an exercise for you to do. Write them in order. You can see roughly where the mean is in the middle, and you can see that kind of spread on average of just over 2 marks going out in either direction, forwards and backwards from that mean. Now, we're going to look at what happens when we have grouped data next. You'll remember that we find the mean by summing up the x values and divided by n. But when we have group data in a table, we have to find the midpoints of the classes, and we call the midpoints x. And our mean is found by summing up the midpoints x times the frequencies and dividing by still n, but we write it as the sum of f, the sum of the frequencies, because that's how many data values we have. Now, we can apply the same ideas here to the variance and the standard deviation formulas. So our variance formula, where before we had the sum of x minus x bar squared over n, we now have the sum of f times that over, instead of n, the sum of f. And for our second version of the formula, the one we said was slightly less tedious to work out, we have, instead of the sum of x squared over n, we do the sum of fx squared over the sum of f. And for the mean, we just use this still. So I could write x bar there, but we've got the sum of fx over the sum of f squared. So that could be written as this. And then, of course, with standard deviation, it's still is the same as before. It's the square root of the variance. So we write the square root of the above, and here the square root of the above. So let's have a look at examples 8 and 9. Example 8 is a frequency table, not group data in this one. So it's worth pointing out here that this is not just for group data, but this is for any frequency table. So here we've got ungrouped data. The time spent out of school, these are our x in minutes during the lunch hour this is measuring. So these are our x values, these are our f values. So first of all, we're going to do, for the first part of the formula here, the sum of fx squared. Now, if you wanted to, you could add some extra columns on here to help you work this out. I'm going to do it this time, but bear in mind you don't have to. It just makes it a little bit clearer when we've got a lot going on. So we're going to need fx, and we're going to need fx squared. So fx is 3 times 35, 36 times 17, 37 times 29, and 38 times 34. Fx squared, please be very careful here, you only square the x's, not the f's. So we're going to do 3 times 35 squared. So it's squaring the 35 and then timesing by 3. So that gives us 3675. Then we've got 17 times 36 squared, 22032. 29 times 37 squared, and 34 times 38 squared, 49096. It's really time consuming to work out. So we have got the sum of fx squared is going to be the sum of all of these here. So that is 114,504. There's one I made earlier. The sum of fx is going to be the sum of all of these. That's 3,082. And the only other thing we need in our formula, sum of fx squared we've got, sum of fx we've got, the only other thing we need is the sum of f. And the sum of F, if you add them all up, is 83. So there were 83 students that took part in this survey. So our variance is, always write out the formula, sum of fx squared over sum of f minus the mean squared. So that's 114,504 over 83 minus 3082 over 83, but that one is squared. And that gives us 0.74147 and so on. Let's get that on the calculator just so you can see. We've got 114,504 over 83 minus 3082 over 83 squared. 0.7147 and so on. That's our variance, and our standard deviation is the square root of the variance which is 0.861. What are the units? This was the minutes spent out of school, so that many minutes to 3 significant figures. Let's stop and take a second to make sure we know exactly what this number means, because the hardest thing with standard deviation is not the laborious calculations, it's understanding what on earth it's on about. So what we're saying is the mean time spent out of school, well, that would have been the sum of fx over the sum of f. Let's just make a little note of that here so we can see the number, 3083 over 83. The mean time spent out of school on the lunch break was 37.1 minutes. So the average time spent out by students was that. So that's around about here. But all of those times there had an average spread away from this mean of about 0.86 minutes. And you can see that here. They're not actually that spread out from 37 minutes. It only goes down to a few of them at 35 and a lot of them at 38. So we're actually less than a whole minute away from 37.1 on average. So we can see that we've got the average time, but that all of the others are not particularly spread far away in terms of their spread from that average. Finally, let's have a look at example 9. So it's the same kind of idea, but with a grouped table. So the only thing we've got to remember here is that our x values are the midpoints of each of these classes. So our x values are respectively 2.5, 7.5, 12.5, 17.5, 40 and 65. Now, we would need to do the same thing here as we did previously on this table, in that we would have to now work out f times x. So 4 times 2.5 is going to be 10, and this one is going to be 112.5. 5 times 12.5 would be 62.5. 2 times 17.5 would be 35. 0 times 40 is 0, and 1 times 65 is 65. Next one I can't do in my head, so let's get the calculator. We've got to do fx squared, so we square the x value and times it by the frequency. 2.5 squared times 4 is 25. 7.5 squared times 15 is 843.75. 12.5 squared times 5 is 781.25. Then we've got 17.5 squared times by 2, 612.5. Next one's easy because we're going to have 40 squared times by 0, so that's just going to be 0. But then we have got 65 squared times by 1, 4,225. Once we've got those, we've done all the hard work. We've got the sum of fx squared, so that's adding up this row here. I've run out of space, otherwise I would put it at the end there. So that's going to be 6,487.5. The sum of the fx row, all of these, is 285.5. And the sum of the frequencies, that's all of these here, was 27. I didn't say at the start, by the way, these were the length in minutes of telephone calls that Andy made for a month. So he's made 27 calls in the month, and these are all the lengths of those 27 calls. So our variance first is the sum of fx squared over the sum of f minus the mean. I'm going to do it differently this way, so you can see that in both ways, minus the mean squared. Now there's no different to this. That was also the mean, sum of fx over the sum of f. So what I'm going to do here is work that out first. The mean is the sum of fx over the sum of f. So that's 285 over 27. So that's 95 over 9, or 10.5 recurring. So his average, his mean call length was 10.5 minutes. So our variance, it's going to be 6487.5 over the sum of f, 27, minus our mean squared. I'm keeping that number on the calculator screen so that I don't lose it, because I need to work it out exactly. So I'm going to go 6487.5 over 27 minus the mean squared, and I get a variance of 128.858. And these calls were in minutes, so that's going to be in minutes squared, which doesn't really mean a huge amount. So let's find the standard deviation, which is the square root of the previous answer. And that's going to be 11.4 minutes. So again, let's think about the context. Let's make sure we know what's going on. These calls, 27 calls that Andy made in a month. The mean time he spent on a call was just over 10.5 minutes, but the calls were on average spread out by 11.4 minutes from there. Now, the interesting thing, of course, with that is, if you take 11.4 from 10.5, you're going to go into negatives. And that's impossible, but look at the data. You have from 10.5 around out here, you've got this one, look, 60 to 70 minutes, and that one's skewing the data a lot. So that one is not only dragging up the mean, because most of the calls were between 5 and 10 minutes, but it's also affecting the standard deviation. So it goes to show that when we were talking about percentile ranges, interpercentile ranges and interquartile ranges in the last video, we said they were great because they ignore extreme values. The mean and the standard deviation use all the values. So if you've got extreme values, they are affected by them. So it's worth bearing in mind when certain types of interpercentile ranges or the standard deviation, where certain types of measures of spread are useful and when they're not. And generally, if you've got extreme values, then the standard deviation and the mean are less reliable than the median and the interquartile range. So now you can have a go at exercise 2E.